Welcome Engineering Statics. This is ENGR ampersand 214, and this is our second example of particle equilibrium. And just to review, static equilibrium of a particle means first you have to have a particle, which means you've got a body which is very small and can't support moment, isn't big enough to have an R for R cross F, and second, the sum of the forces or the net force in all three orthogonal directions has to be zero. F equals ma, so A non-acceleration or static equilibrium only occurs when F is zero, F net. So in this case, we got a 3D problem, and we've got a ball with a weight. It weighs 10 newtons, and it's got a couple of other forces acting on it, and we don't know the geometry per se, but we've been given the forces, and these are vectors, even though there's not an arrow or bold. I've limited in my fonts here on my whiteboard. But we have a vector force A, which is providing 5 newtons in the I hat direction, 10 newtons in the J hat, and negative 30 in the K hat. We got another force offering us 2 newtons in the I hat, 3 newtons in the J hat, and positive 4 newtons in the K hat. And we're asked what third force vector, if any, is needed to keep the particle from accelerating. So first, maybe it is in static equilibrium, and if it's not, we need to find out how to get it there. So like for most things, let's go ahead and start with, well, we can't really start with an FBD as easily because it's very hard to envision these force vectors. So instead, we're going to jump for once right to equations of equilibrium, and grab my writing implement here, and we're going to start tallying directly up, and we're going to use our vector algebra principles to add things up a little bit easier. So first we start with our force tally. We have a weight force, and we can draw arrows now, equals negative 10 newtons, and I'm going to assume, I'll just draw myself a little coordinate axis. I'm going to assume that gravity is acting in the K hat direction. It could be acting in any orthogonal direction, but I'm going to assume, I'll put a little G here to say gravitational acceleration is the downward K hat. So we have 10 newtons of weight acting in the negative K hat direction. And we've also got force A is providing us 5 newtons, I hat, 10 newtons J hat, minus 30 newtons K hat, and force B is giving us 2 newtons, 2 newtons, in the I hat direction, negative 3 newtons in the J hat direction, and positive 4 newtons in the K hat. So we can write an expression directly for the net force on that particle, F net, by just adding up all of the components of all of the vectors in each of their 3 orthogonal directions. And this is where vector algebra expression is really handy. So we don't have to take geometric, you don't have to use any trig to find components in the x and the y. It's already been done for us. We have the unit vector directions and the magnitudes of the force in each one of them. So let's scan through and just collect all of, in fact, we'll use some colors here. I'll use red to collect all of the I hats. So we got 5 and 2. So that should be 7 newtons total in the I hat direction. I have 10, positive 10 minus 3 in the j hat, so that is again a total of 7 and positive 7 newtons j hat. And for k hat, I have negative 10, negative 30, so that gives me a negative 40, plus 4 is negative 36. 36 newtons k hat. Well, let's see. This doesn't look like it equals 0 to me. In fact, it's got a net force in every single orthogonal direction, so it's going to accelerate in each of the directions. So it is absolutely not at static equilibrium. So to make F net 0, we need to make each one of these 0. So what would we add? We'd add an FC, call it, of negative 7 newtons in the I hat, minus 7 newtons in the j hat, plus 36 newtons in the k hat. So that F net plus FC equals 0, which is the condition for equilibrium. And that's it. This is, I'll circle it in green, or I'll rewrite it down here in green, FC of negative 7 newtons in the I hat direction, negative 7 newtons in the j hat direction, and positive 36 newtons in the k hat direction is what we would apply to put this ball, which we are treating as a particle, into static equilibrium, given that it has a weight of 10 newtons and it had these two forces already being applied. So we're done. And again, this is a great example of why vector algebra can really simplify a problem if you can use it to express all of your force directions and magnitudes. And that is a 3D example of particle equilibrium to complement all of your 2D examples. And that's it for this example.